Something is wrong with the universe. Not a small thing, not a rounding error. A telescope launched into deep space has been sending back images that stop scientists mid-sentence. Galaxies that formed too fast, structures that are too large, an expansion rate that simply does not match our best models. We thought we had a map. James Webb showed us the map was wrong. Tonight, we travel from the edge of what is visible to the heart of what cannot yet be explained. A web of dark matter stretching across billions of light years. A cosmic tension that two Nobel Prize-winning teams cannot resolve. And a shape to reality that nobody predicted. If you enjoy this journey, consider subscribing. We do this every week. Take a breath. We launch into the deep. For most of human history, the universe was just the sky above us. Then we built better eyes. Telescopes pointed upward, revealed planets, then distant stars, then smudges of light that turned out to be entire galaxies. Each discovery pushed the known universe further back, wider, deeper. And with each push, scientists worked to build a model, a framework, a map of everything. By the late 20th century, cosmologists believed they had something close to a complete picture, solid, though imperfect. The universe, they said, began roughly 14 billion years ago in an event called the Big Bang. From a single, unimaginably hot point, everything exploded outward. Space itself stretched. Matter cooled. Gravity pulled hydrogen into the first stars. Stars forged heavier elements and died in enormous explosions, seeding the next generation. Galaxies formed, clusters of galaxies formed, and over billions of years, all of that matter arranged itself into a vast, web-like structure called the cosmic web. That was the picture. It had names, it had equations, it had predictions. The model even had a shape for the universe. According to the best measurements available at the time, space on the largest scales is flat. Flat in the geometric sense, like a perfectly level plane extending forever. If you drew a triangle across millions of light years, its angles would add up to exactly 180 degrees. The universe, according to this model, plays by the rules. It is predictable. It is knowable. Scientists called this framework the standard model of cosmology. It explained the ancient glow of leftover radiation from the Big Bang, called the cosmic microwave background. It explained why hydrogen and helium are the most common elements. It explained the large-scale distribution of galaxies. The model worked so well that most physicists trusted it completely. There was just one problem. It was built on incomplete information. Every observation that confirmed the model came from telescopes that could only see certain kinds of light. Visible light, some infrared, enough to see the universe as it is today, or as it was a few billion years ago. To see the universe as it was in its earliest chapters, you need to look much further back, and to do that, you need a completely different kind of eye. As the universe expands, the light from the most distant objects gets stretched. The further away something is, the more its light shifts toward the red end of the spectrum, and eventually beyond red, into the infrared, light that no human eye and no previous telescope could capture. Light that carries information from the first 500 million years of existence, the most formative period in cosmic history. For decades, that chapter was dark. Scientists made predictions about what those early galaxies must have looked like. Small, faint, young, and still forming. They were so confident that when a new telescope was finally designed to see that lost light, most scientists expected it to confirm what they already believed. Instead, it found something else entirely. The first images arrived in July of 2022. Scientists scrolled through data that had taken decades of work and $10 billion to collect. And then, almost immediately, something felt off. The galaxies in those early images were massive, bright, and structured in ways that should have taken billions more years to develop. The map was wrong in a way that nobody had anticipated, but what came next was even stranger. Before we go further into what Webb found, you need to understand what it is. James Webb is a fundamentally different machine, built to answer questions that older telescopes could not even ask. The Hubble Space Telescope, launched in 1990, changed astronomy forever. It captured images so sharp and so deep that they became part of how humanity pictures the cosmos. The famous deep field image, a photograph of a tiny patch of sky no bigger than a grain of sand held at arm's length, revealed thousands of galaxies hiding in what appeared to be empty space. Hubble showed us that the universe is crowded beyond imagination. Hubble had a ceiling. It was designed to capture visible light and some ultraviolet. The deeper into the universe you look, the more that visible light gets stretched out of range. By the time light from the very first galaxies reaches us, it has been traveling for over 13 billion years. Space has stretched so much during that journey that the light arrives as infrared radiation. Invisible to Hubble, invisible to everything that came before, Webb was built for exactly that light. Its primary mirror stretches nearly 22 feet across, almost 3 times the size of Hubble's. The mirror is coated in a microscopically thin layer of gold, because gold reflects infrared light with exceptional efficiency. The entire telescope sits behind a sunshield the size of a tennis court, made of 5 layers of material as thin as a human hair, designed to keep the instruments at temperatures hundreds of degrees below zero. Infrared detectors only work when they are extraordinarily cold. Any warmth, even the faint glow of the telescope's own structure, would drown the signal in noise. Webb's cooling system operates at temperatures close to absolute zero, colder than almost anything that exists naturally in the observable universe. Webb orbits around our star at a point 1 million miles from Earth, at a gravitational sweet spot called the second Lagrange point. There, the telescope drifts in permanent shadow, always facing away from the light of our star, Earth, and Moon simultaneously. It is the coldest, darkest, most stable vantage point achievable. To get there, Webb had to fold itself into a rocket like origami. Its mirror consists of 18 hexagonal segments of gold-coated beryllium, each adjusted by tiny motors to fractions of the width of a human hair. This took weeks after launch to achieve. The entire process was so delicate that engineers described the deployment as having 244 single points of failure, each one capable of ending the mission. It worked. Webb can detect the heat signature of a bumblebee at the distance of the Moon. It can see a candle flame from 1 million miles away. In practical terms, it can look back to within just a few 100 million years of the Big Bang and see individual galaxies forming in real time, something no instrument in human history has ever done. The scientists who designed Webb made specific predictions about what it would find. Early galaxies, they said, should be small, chaotic, and dim. The universe was young. Things had not had time to organize yet. Webb pointed its golden mirror at the deep sky and looked. What it saw left the entire field of cosmology scrambling for answers. July 12, 2022. The National Aeronautics and Space Administration released the first full-color images from the James Webb Space Telescope to the world. The images were beautiful. That part was expected. A deep field image packed with thousands of galaxies, each one a different shape and color, a dying star wrapped in glowing rings of ejected gas. The collision of 2 galaxies caught in the act, the atmosphere of a distant planet, analyzed in detail for the first time. Inside the scientific community, something else was happening alongside the celebrations. The galaxy images contained objects that did not fit. The kind of mismatch that made senior astronomers read the data twice, then a third time, then call their colleagues. The objects in question were galaxies. Ancient galaxies, seen as they appeared when the universe was only a few 100 million years old. long before they should have had time to mature. And they were big, large by the standards of modern galaxies, not just young ones. Some appeared to have as much mass as our Milky Way galaxy, or more, fully formed, organized, rotating, structured. Under the standard model of cosmology, that is close to impossible. The reason comes down to time. To build a galaxy of that size, you need gravity to pull in enormous amounts of hydrogen gas, ignite it into stars over hundreds of millions of years, have those stars live and die, and repeat the cycle over and over until you accumulate enough mass and structure. It takes time, more time than the universe had available when those galaxies were already formed. Ivo Labbé, an astronomer at Swinburne University in Australia, was one of the first to flag the problem. His team found what appeared to be 6 massive galaxies in the early universe that would represent more mass than the standard model predicts should have existed in that entire region of space at that age. He described the finding as something like discovering a fully grown adult human in a nursery. It did not break a rule slightly. It broke it dramatically. Paolo Santini, an astronomer at the National Institute for Astrophysics in Italy, described the early Webb data by saying the results were simply not expected. The reaction across the scientific community was a mix of excitement and genuine alarm. For decades, the standard model had been tested from every angle and had held. Now, here were objects, dozens of them, casually existing in the early universe as though the rules simply did not apply. Some researchers suggested measurement errors. Maybe the distances were wrong. Maybe the instruments, brand new and still being calibrated, were introducing some systematic mistake that would smooth everything out with time. The data kept coming in. More images, more spectra confirming distances, more mass calculations that could not be explained away. The objects were real. They were where Webb said they were. The standard model had survived everything cosmologists had thrown at it for 50 years. It had been stress-tested by satellite observatories, by ground-based surveys, by decades of competing teams pushing their instruments to their limits. It had not survived the first year of James Webb, and yet the early galaxies were only the beginning of what the telescope was about to reveal. In the chapters that followed, every new image added to the weight of the same impossible question. To understand why those early galaxies caused such a crisis, imagine you are building a city from scratch. You start with empty land. You lay foundations. You pour concrete. You frame walls. You install plumbing and electrical and glass. Each step takes time, and each step depends on the one before it. No city has ever appeared fully built overnight. The process has a minimum speed. You cannot compress it indefinitely, no matter how many workers you add. Galaxy formation works on the same logic. After the Big Bang, the universe was a nearly smooth, nearly uniform sea of hydrogen and helium gas. There were tiny variations in density, regions slightly denser than others. Gravity pulled on those denser regions, drawing in more gas, making them denser still. Over hundreds of millions of years, the gas collapsed into the first stars, which burned fast and died explosively, seeding the next generation. Slowly, gravity assembled clumps of stars into proto-galaxies, which merged and grew across billions of years into the galaxies we see today. That process has a minimum timeline. Physicists have calculated it carefully. It is built into the standard model. And then Webb looked back to a time when only a few 100 million years had passed since the Big Bang, and found cities, fully built, mature, enormous. In August of 2022, a team of astronomers identified candidate galaxies from the very early universe that appeared far too massive and far too structured to exist at that age. One object had an estimated mass roughly equivalent to one of the largest galaxies in the modern universe, seen when the universe was less than 500 million years old. That is a fraction of the time current models say is needed to build something like that. The numbers were so extreme that several researchers initially assumed contamination. Perhaps the objects were closer than they appeared, but as more Webb data came in and spectroscopic analysis confirmed the distances, those explanations fell away. By 2023 and into 2024, the findings were a pattern. Webb was consistently finding early universe galaxies that were too big, too bright, and too organized. 300 unusually luminous objects identified by a team at the University of Missouri. Multiple independent teams confirming the same result from different datasets. One possible explanation: star formation in the early universe was far more efficient than current models allow. Perhaps in the dense, turbulent conditions of the young cosmos, gas collapsed into stars at a rate our models have never accounted for. The standard model would need updating, but it might survive. Another explanation is more unsettling. Perhaps the standard model is missing something fundamental: a different behavior of dark matter, a different relationship between gravity and density on those scales, some ingredient we have not yet named. The honest answer, confirmed by multiple research teams and acknowledged openly by the scientists involved: we do not yet know. What we do know is that the universe built something massive in a fraction of the time we thought possible. It assembled galaxies at a scale and maturity that our most sophisticated models, running on the world's most powerful computers, cannot reproduce. And the question of how it did, that leads directly to the hidden structure underneath everything. A structure that James Webb has now seen in ways no telescope ever has. Close your eyes for a moment and picture the universe. Most people picture darkness, scattered points of light, stars drifting in empty space, loosely clustered here and there, essentially random, like glitter thrown across a black table. That picture is completely wrong. The universe, on its largest scales, is one of the most intricate structures in existence. A three-dimensional web of filaments, nodes, and vast empty voids that stretches across everything we can observe, and almost certainly far beyond it. Scientists call it the cosmic web. Imagine a spider's web built across billions of light years of space. The threads are long chains of galaxies, drawn together by gravity and by the invisible scaffolding of dark matter beneath them. Where threads cross, enormous clusters of thousands of galaxies gather into dense, blazing nodes. Between the threads, there is almost nothing. Enormous voids, some stretching hundreds of millions of light years across, where almost no galaxies exist at all. Just expanding space. The cosmic web was predicted theoretically before it was confirmed by observation. In the 1980s and 90s, large-scale surveys began mapping the positions of galaxies across the sky, and the pattern became undeniable. Galaxies were not randomly distributed. They formed walls, filaments, and clusters. The universe had large-scale structure, a skeleton. This discovery changed cosmology. Gravity, dark matter, and the initial conditions set at the Big Bang had conspired over billions of years to weave everything into this single, connected structure. Here is what made James Webb so important for understanding the cosmic web. The web we could observe before Webb was the web as it exists today, or as it existed a few billion years ago. We could see the mature result, but we could not see the process. We could not watch those first threads being drawn together in the earliest chapters of cosmic time. Previous telescopes lacked the infrared sensitivity to see that far back. The infant universe was invisible to us. Webb changed that, and what it found in the early cosmic web was startling. Structures that should have taken far longer to assemble were already there, already threaded together, already pulling matter into patterns that mirror the cosmic web we see billions of years later. This raises a question cosmologists are still wrestling with. If the web was already taking shape that early, the conditions that produced it must have been set into motion even earlier, before the first stars, before the first galaxies. Possibly within the first moments after the Big Bang itself. The web may be the universe's most fundamental organizing principle. Everything we see, Every galaxy, every cluster, every filament of light is arranged along a structure that formed in the deepest darkness before almost anything else existed, and Webb has now found the earliest thread of that structure ever seen. Think about what that means. The universe, at less than 7% of its current age, was already building something that mirrors the largest architectural feature we can observe today. The scaffolding was going up before the walls, before the rooms, before anything we would recognize as a finished structure. Whatever process drives the formation of the cosmic web operates faster, deeper, and stranger than any model we have built has managed to describe. And the closer Webb looks at those earliest threads, the stranger the picture becomes. 830 million years after the Big Bang, something extraordinary was already in place. A thread, a filament of 10 galaxies, stretched across 3 million light-years of space, aligned along a single axis, already organized, already gravitationally bound, already behaving exactly like a mature strand of the cosmic web, and at its heart, a blazing quasar, a galaxy with a supermassive black hole at its center, devouring matter and radiating light across the universe like a lighthouse. James Webb found this structure and confirmed it in detail that no previous telescope could have achieved. The team behind the discovery, part of a program called ASPIA, was studying the environments of the earliest known black holes. They expected to find some loosely associated galaxies. They did not expect to find a filament of that length, that narrow, and that clearly organized. Xiao Hui Fan, an astronomer at the University of Arizona who was part of the team, said he was surprised by how long and how narrow the structure was. He expected to find something, but not a structure that clean. 3 million light-years is a staggering distance to put in perspective. Our entire Milky Way galaxy spans roughly 100,000 light-years from edge to edge. This filament is 30 times longer than our galaxy is wide, and it existed when the universe was less than 7% of its current age. Under the standard model, the cosmic web is expected to grow gradually. Early filaments should be faint, short, barely distinguishable from the surrounding noise of young galaxies. They should strengthen and lengthen over billions of years as gravity draws more matter in. A filament, this well-defined, this long, and this organized at such an early age, pushes against what the standard timeline predicts. The structure is anchored by something remarkable. That quasar at its center harbors a black hole with a mass somewhere between 600 million and 2 billion times the mass of our star. To grow a black hole that massive in that amount of time, two things must happen simultaneously. It must have started from an already massive seed, and it must have been consuming matter at the absolute maximum rate physically possible for its entire existence without pause. Neither condition is easy to explain. Both together are deeply puzzling. This discovery suggests the cosmic web did not slowly assemble itself over billions of years the way the models predicted. It appears to have organized with a speed and efficiency that our current understanding of gravity and dark matter does not account for. This is confirmed science. The filament is real. The distances are confirmed. The black hole masses are measured. What remains unknown is the mechanism that produced it all so quickly. The answer almost certainly lies in the nature of the invisible substance that makes up the majority of all matter in the universe. A substance that Webb is now mapping with a clarity never achieved before. And for the first time, that mapping is revealing details that do not match 3 decades of assumptions about what dark matter actually is. What that mapping revealed is something that nobody in the field saw coming, something that challenges the most fundamental assumption that cosmologists have been making about the nature of dark matter for over 3 decades. Most of the universe is invisible. That sentence sounds dramatic, but it is simply true. When astronomers add up all the stars, all the gas clouds, all the planets, all the dust, everything in the universe that emits or absorbs light, They account for only about 5% of the total mass and energy that the universe must contain to behave the way it does. The other 95% is missing from that accounting. About 27% of the universe, by current estimates, is dark matter. Dark matter does not emit light. It does not reflect light. It does not absorb light. It passes through ordinary matter like a ghost passes through a wall. You cannot touch it, see it, or measure it directly with any instrument ever built. The only reason we know it exists is because of what it does to everything around it. Its gravity. Galaxies rotate too fast to hold together, based on the visible matter inside them alone. Galaxy clusters bend the light from behind them far more strongly than their visible mass could produce. The large-scale structure of the universe, that cosmic web of filaments and voids, matches the predictions of a universe filled with dark matter. Remove it from the models and the web disappears. Nothing holds together. Nothing makes sense. So, dark matter exists. That part is as confirmed as anything in modern physics. What it actually is, at a fundamental level, is one of the deepest unsolved problems in all of science. For decades, the leading theory has been that dark matter consists of cold, heavy, slow-moving particles. Scientists call this the cold, dark matter model. Under this model, dark matter clumps into small, compact structures first, and those structures gradually merge into larger ones. The cosmic web grows bottom up, from small to large, over long stretches of time. This model, when plugged into simulations, produces a universe that looks remarkably similar to the one we observe. Or it did, until Webb started looking at the early universe in detail. In December of 2025, a team of researchers, including scientists from Harvard, the Massachusetts Institute of Technology, and Arizona State University, published a paper in the journal Nature Astronomy examining the shapes of early galaxies as seen by Webb. What they found was unexpected. Those early galaxies were elongated, stretched. They looked like cosmic cigars rather than cosmic pancakes. And this shape does not match cold, dark matter model predictions. What it does match is something called warm dark matter, or a more exotic possibility called wave dark matter. In these models, dark matter flows along smoother, longer filaments. Galaxies forming in this environment would naturally develop those elongated shapes. This is still a theory. It is not confirmed, but it is supported by multiple independent lines of evidence now emerging from Webb data. If dark matter is not cold, if it behaves more like a smooth fluid or a quantum wave, then the fundamental scaffolding of the entire universe is different from what we have been assuming for 30 years. Every simulation of galaxy formation ever run, every prediction about the size and shape of galaxy clusters, every model of how the cosmic web grew, all of it built on an assumption that may be wrong, and that changes everything downstream from it. Shape is not just cosmetic. In the universe, the shape of a galaxy is a record of how it formed. A galaxy that grew slowly by pulling in matter from all directions in a smooth, symmetric way will look round or disc-like. A galaxy that formed along a filament, shaped by material streaming in from one direction, will look stretched, elongated, like it was poured into a mold rather than assembled from all sides. When James Webb began imaging the earliest galaxies, the shapes were immediately unusual. A consistent pattern across dozens and then hundreds of early objects. These galaxies were elongated at a rate far higher than the cold, dark matter model predicts. The standard simulations, running on the most powerful computers in the world and refined over decades, produce galaxies at that age that look compact and roughly spherical. Webb kept finding long, thin structures. The team, led by Alvaro Pozo at the Donostia International Physics Center, working with colleagues from the Massachusetts Institute of Technology, Harvard, and Arizona State University, ran the most detailed comparison yet. They took Webb images of early galaxies from the JADES survey, one of Webb's most ambitious deep field programs. and compared the observed shapes directly to 3 different sets of simulations, one using cold dark matter, one using warm dark matter, and one using wave dark matter. The cold dark matter simulations consistently produced galaxies that looked too compact compared to what Webb actually sees. The warm and wave dark matter simulations produced elongated shapes that matched the observations far more closely. The conclusion was statistically significant and pointed clearly and consistently in one direction. Rogier Windhorst, a professor at Arizona State University and an interdisciplinary scientist for the Webb mission, described the finding by saying, "Webb suggests the earliest galaxies may be embedded in marked filamentary structures that smoothly join the star-forming regions together. That kind of smooth joining is a characteristic of warm or wave dark matter. To understand why this matters so deeply, consider what the cold dark matter model predicts. It predicts the universe should be filled with enormous numbers of small, compact, dense clumps of dark matter. These clumps should have seeded the formation of small galaxies first. Those small galaxies should then have merged into larger ones over time. Every step in that ladder depends on the initial clumpiness. If dark matter behaves more like a smooth fluid or a quantum wave, those small clumps do not form the same way. The bottom rungs of the ladder are different, and every prediction built on top of the cold dark matter model about how galaxies form, how clusters grow, how the cosmic web develops, needs to be revisited. This is an active debate. Alternative explanations exist. Researchers are clear about that. The consistent signal across multiple data sets, all pointing toward the same shape anomaly in early galaxies, is something the field is taking very seriously. The shape of a galaxy is not random. It is an inscription, a record written in stars and gas of the conditions under which it was born, and Webb is reading those inscriptions from the earliest pages of cosmic history. A completely different crisis is playing out at the scale of the entire universe, and it has been building for over a decade. The universe is expanding. That has been known since the 1920s, when astronomer Edwin Hubble observed that distant galaxies were moving away from us, and the further they were, the faster they receded. It was one of the most consequential discoveries in the history of science. The universe was growing. The rate at which it grows has a name: the Hubble constant. In simple terms, it tells you how fast 2 points in space are moving apart as the universe expands. Measuring it precisely is one of the most important tasks in cosmology. It tells us how old the universe is. It tells us how it will evolve. It tells us the ultimate fate of everything. For decades, 2 different methods existed for measuring this rate. And for decades, there was a lingering fear in the scientific community that one day those 2 methods might disagree in a way that could not be explained away. That day came. The first method looks at the early universe. Scientists study the cosmic microwave background radiation, the faint glow left over from the Big Bang itself, and use the detailed patterns within it to calculate what the expansion rate should be today, based on the standard model. This method gives a lower number. The universe, according to this approach, should be expanding at a rate of roughly 67 kilometers per second per megaparsec. A megaparsec is about 3.25 million light years. The second method looks at the nearby universe. Scientists use objects of known brightness, Cepheid variable stars, and type Ia supernovae to measure distances directly and calculate how fast those distances are growing. This is the direct measurement method, built step by step along what cosmologists call the cosmic distance ladder. It gives a higher number, roughly 72 or 73 kilometers per second per megaparsec. Those 2 numbers should be the same. They are measuring the same universe. There is no physical reason they should produce different answers, yet they do, consistently, across many independent teams, using many different instruments. The gap between them, approximately 8 to 9%, is what scientists call the Hubble tension. It has been growing more troubling with every passing year as measurements become more precise. A more precise measurement that still shows a discrepancy is not reassuring. It is the opposite. One obvious explanation was measurement error. Perhaps one of the two methods had a systematic flaw, an instrument miscalibrated, some subtle mistake in the math. If that were true, the tension would dissolve once someone found the error. Everyone hoped that was what was happening. Then, James Webb pointed its infrared eye at the distance ladder and began checking the work. Nobel laureate Adam Rees, the physicist at Johns Hopkins University who won the Nobel Prize for co-discovering that the universe's expansion is accelerating, led the effort. His team used Webb to verify measurements of Cepheid variable stars in distant galaxies, the rungs on the cosmic distance ladder, with a precision that no previous instrument could achieve. Hubble was right. The measurements were accurate. Every rung of the distance ladder was precisely where it had always been. The Hubble tension was real. The universe was genuinely expanding faster than the standard model predicted, and nobody could explain why. What came next made it worse. When a scientist finds a discrepancy in their data, the first instinct is always to look for the mistake. Check the instrument, rerun the calculation, look for contamination in the sample, re-examine the assumptions built into the measurement. Science progresses by eliminating errors, and most apparent discrepancies in physics turn out to be exactly that: errors. Someone measured incorrectly, a calibration drifted, a model contained a hidden assumption that was not quite right. For years, that was the hope with the Hubble tension. One of the two measurement methods must be wrong. Because the direct measurement method, the one using Cepheid stars and supernovae to climb the cosmic distance ladder, was the newer and more complex of the two, it was the natural candidate for suspicion. Perhaps in crowded star fields, where Cepheids are difficult to isolate, Hubble's measurements were being contaminated by the light of neighboring stars. James Webb was designed, among other things, to test exactly this. Its infrared sensitivity and its ability to resolve individual stars in crowded fields with extraordinary sharpness made it the perfect instrument to check whether Hubble had been making systematic errors in its Cepheid measurements. The results, published in February of 2024 in the astrophysical journal Letters, were definitive. Webb confirmed Hubble's measurements across multiple independent approaches. The team used Cepheid variable stars, carbon-rich stars, and observations of the brightest red giant stars in the same galaxies, all pointing to the same conclusion. The Hubble Space Telescope had been right all along. Adam Rees, whose Nobel Prize came from co-discovering the accelerating expansion of the universe, described the finding plainly. With measurement errors eliminated, what remains is the real and exciting possibility that we have misunderstood the universe. A subsequent study published in December of 2024 used the largest sample of Webb data collected in its first 2 years to repeat the analysis with even greater precision. The result was the same. The Hubble constant, measured by direct observation of the nearby universe, came out at approximately 72.5 kilometers per second per megaparsec. The value predicted from the early universe remained near 67. The gap had not closed. The measurements were not converging. They were confirmed. The scientific implications are enormous. Either something is wrong with the standard model of cosmology at a fundamental level, or the universe contains some feature that current physics simply does not account for. Among the possibilities, scientists are now seriously considering a form of energy in the early universe, sometimes called early dark energy, that gave an unexpected acceleration to expansion in the first moments after the Big Bang, before fading away. This could explain why the early universe measurements predict a lower expansion rate, while the current universe runs faster. Another possibility is even more unsettling. Perhaps dark energy, the mysterious force driving the universe's accelerating expansion, is not constant. Perhaps it changes over time. Perhaps the rules of physics themselves, the constants we assume are fixed throughout all of space and time, are not as fixed as we have assumed. At a meeting of the American Astronomical Society in January of 2025, astrophysicist Dan Skolnick of Duke University stood before his colleagues and said something that would have been unthinkable a decade earlier. The Hubble tension, he said, is now a crisis. Every field of science has a foundation, a set of core principles proven through decades of observation and experiment that everything else is built upon. In cosmology, that foundation has a name. Scientists call it by a shorthand name, combining the cosmological constant and cold, dark matter. Lambda refers to the cosmological constant, the term that represents dark energy in Einstein's equations of general relativity. The cold, dark matter component describes the invisible substance that provides the gravitational scaffolding of the universe. Together, the model describes a universe that began with the Big Bang, expanded and cooled, formed structure through the gravitational influence of cold, dark matter, and is currently accelerating in its expansion due to dark energy. This model has been tested against an extraordinary range of observations: the temperature patterns of the cosmic microwave background, the distribution of galaxies across large scales, the abundances of light elements produced in the first minutes after the Big Bang. In every test, across 50 years of data from dozens of independent experiments, the model passed. It is one of the most precisely tested frameworks in the history of science. Scientists have thrown everything at it, and it has held up. Every independent test, every new observation, every competing team has confirmed it, generation after generation, until recently. And yet, Webb's discoveries are stacking up against it. One anomaly can be explained. Two can be a coincidence. The list of observations that do not fit has grown substantially in just a few years. The Hubble tension is confirmed. The expansion rate is genuinely discrepant between early and late universe measurements, and Webb has ruled out instrument error as the cause. This alone would be enough to demand serious revision of the model. The early massive galaxies are real. Dozens of objects in the early universe are too large, too bright, and too structured for the cold, dark matter model's timeline. The shapes of early galaxies point away from cold, dark matter toward warm or wave dark matter, suggesting the fundamental nature of the invisible mass holding the universe together is different from what was assumed. 300 luminous objects discovered by the University of Missouri team in 2025 defy explanation under current models of galaxy formation. The brightness of these objects is inconsistent with what standard galaxy formation physics predicts for that era. And then there are the little red dots, a category of object discovered exclusively by Webb in the early universe that does not cleanly fit any existing classification. They are small. They are intensely red. They are surprisingly bright for their size. And some of them may not be galaxies at all. Over 500 researchers have now come together in a collaboration called Cosmoverse to examine the various tensions between the model's predictions and current observations. Their collective conclusion is that these discrepancies are too consistent and too numerous to attribute to measurement error. Something is genuinely missing from our understanding of the universe. What is missing is unknown. It may be a new form of energy in the early universe. It may be a different kind of dark matter. It may be something that does not yet have a name. What is certain is that 300 luminous objects found by Webb, impossible under current models, are not going away. In August of 2025, a team of astronomers at the University of Missouri published a study that described something remarkable and deeply unsettling. Using infrared images from James Webb, they had identified 300 objects in the early universe that were brighter than they should be, brighter in a way that current models of galaxy formation cannot account for. The team used 2 of Webb's most powerful infrared cameras to scan deep into the early universe, searching for objects whose light had been stretched by the expansion of space into the infrared range. They applied a technique called dropout analysis, which identifies objects based on how their light behaves at specific wavelengths, to isolate candidates from the very early universe. What they found was a population of objects that lit up with a luminosity that standard physics does not predict for that era. Haojing Yan, an astronomy professor at the University of Missouri and a co-author on the study, was careful to describe the objects as candidates. Confirming their exact nature requires further spectroscopic observation, which takes time and telescope access. Even as candidates, the objects are significant. If even a few of them turn out to be what the team suspects, the study would challenge current ideas about how galaxies formed in the earliest period of cosmic history. The brightness problem connects directly to the earlier puzzle about galaxy size. A galaxy that is brighter than expected is also likely more massive than expected. More stars burning, more energy being released, more structure already in place. These 300 objects fit the same pattern that earlier Webb discoveries revealed. The early universe was more active, more organized, and more productive than our models say it should have been. One possible explanation: star formation in the early universe was dramatically more efficient than we see today. In the modern universe, when a cloud of gas collapses to form stars, only a small fraction of the gas actually makes it into stars. The rest is blown away by the radiation and winds from the newly forming stars themselves. A process called stellar feedback. If stellar feedback worked differently in the early universe, if those feedback processes were weaker or simply had not had time to develop, then early galaxies could have converted gas into stars far faster and far more completely. The result would be galaxies that are brighter and more massive than the standard model predicts. That explanation is a theory. It has not been confirmed. Another explanation that some researchers find intriguing is that some of these bright objects may not be purely star-forming galaxies. They may be systems where a growing black hole at the center is also contributing enormous amounts of radiation. A galaxy plus black hole system would appear far brighter than a galaxy alone. Webb has already demonstrated in other objects that black holes in the early universe are growing faster than the galaxy formation models allow. What makes these 300 objects so significant is not just their individual strangeness, it is what they represent collectively. Every category of discovery Webb is making in the early universe points in the same direction. More structure, built faster, organized earlier than the standard model predicted. Something was happening in the early universe that we do not understand. Something that made it far more productive, far more organized, and far stranger than any model running today had prepared us for. And there is one category of object that Webb found in that early darkness that does not fit any category at all. They have an unofficial name. Scientists call them little red dots. That name sounds almost playful, almost harmless. But what these objects represent is one of the most disorienting discoveries James Webb has made in its entire mission. Little red dots do not fit neatly into any category that astronomers have ever defined. They are not obviously galaxies. They are not obviously quasars. They may be something the universe has been hiding from us since the beginning, something that previous telescopes were simply not powerful enough to see. Here is what Webb sees when it looks at a little red dot. A tiny object, compact, intensely, almost violently red, and far brighter for its size than any known type of galaxy or black hole system should be at that stage of cosmic history. The brightness to size ratio is what makes them anomalous. A galaxy of that physical scale, at that distance, at that age, should not be putting out that much light. The redness itself is a clue. When light from a distant object gets stretched by the expansion of space, it shifts toward the red end of the spectrum. The redness of little red dots goes beyond simple distance. Their color suggests something extreme is happening inside them. either enormous amounts of dust absorbing and re-emitting light, or incredibly dense concentrations of ionized gas, or some combination of the two that produces a spectral signature unlike anything in our catalogue. In September of 2025, a team of astronomers using Webb data proposed an explanation that reframed the entire puzzle. Their analysis suggested that at least some little red dots may not be galaxies at all. They may be a previously unknown class of object centered on black holes that are growing at rates that defy current physics. Black holes so active, so densely surrounded by infalling matter, that the system as a whole radiates with an intensity that dwarfs the surrounding stars entirely. If that is true, then what Webb is seeing is the engine inside the galaxy, running at a power level we have no framework to explain. The discovery of little red dots connects directly to a broader problem Webb has been uncovering. Black holes that are too big, too early, and too powerful for the timeline our models allow. To understand why that is so alarming, you need to understand how black holes are supposed to grow. Under the standard model, black holes grow by consuming surrounding matter. Gas falls in, spirals down through an accretion disk, and releases energy as it goes. The process has a natural speed limit called the Eddington limit, which caps how fast a black hole can grow based on the radiation pressure pushing back against the infalling gas. A black hole growing at the maximum possible rate still takes hundreds of millions of years to reach certain sizes. Little red dots suggest this limit may be exceeded or circumvented, or that black holes in the early universe had some mechanism for rapid growth that we have not accounted for. This is an active debate. The nature of little red dots is contested, with multiple competing explanations still on the table. The consistency of their appearance across Webb's deep field images, dozens and then hundreds confirmed across multiple survey programs, means they cannot be dismissed as noise. The universe made something in its earliest years that we have never seen before and cannot yet explain. And that is not even the strangest thing Webb found. When it looked at those early black holes, everything has an order. Stars form first from collapsing gas clouds. They live, produce heavy elements, and die. Their remnants seed the next generation. Over time, gravity gathers those generations of stars into proto-galaxies. At the center of each galaxy, a black hole forms and grows alongside it, fed by the gas and dust that the galaxy provides. The galaxy and its central black hole grow together, in rough proportion to each other, across billions of years. That is the story our models tell. It has been supported by observations of the nearby universe, where the mass of a galaxy's central black hole consistently correlates with the mass of the surrounding galaxy's central bulge of stars. The two components scale together. The relationship is tight enough that scientists have used it as a fundamental law of galaxy evolution. James Webb has found that in the early universe, this law does not hold. In December of 2025, a team led by George Reiki at the University of Arizona's Steward Observatory published a study in the Astrophysical Journal examining a galaxy called Virgil, seen as it existed just 800 million years after the Big Bang. What they found inside it was a supermassive black hole accreting material at a rate far beyond what its host galaxy should be able to support. The black hole's mass was far larger than the galaxy's stellar mass would predict under the standard scaling relationship. The black hole had outgrown the galaxy that was supposed to be feeding it. George Reiki described the finding directly. James Webb, he said, has shown that our ideas about how supermassive black holes formed were pretty much completely wrong. Virgil is not an isolated case. Webb has been finding examples across the early universe of black holes that are disproportionately massive relative to their host galaxies. In one case, from 2025, researchers confirmed an actively growing supermassive black hole within a galaxy that existed just 570 million years after the Big Bang. The black hole's mass and growth rate placed it among a class of objects that challenge existing theories at every level. This pattern has a name. Scientists call them overmassive black holes. Their existence in the early universe forces a fundamental question. If the black hole grew before the galaxy, what fed it? In the standard picture, the galaxy comes first, and the black hole is a passenger, growing slowly on the fuel the galaxy provides. If the black hole is outpacing the galaxy, there must be another source of fuel, possibly direct infall of pristine gas from the cosmic web itself, bypassing the galaxy's star-forming regions entirely. Possibly a different mechanism for rapid black hole seed formation that does not require the slow build-up the standard model describes. The implications reach beyond black hole physics. If the central engine of a galaxy forms and becomes powerful before the galaxy does, then the entire sequence of how galaxies are assembled needs to be rethought. The engine does not follow the body. In the early universe, the engine may have come first, and the galaxy may have grown around it. The timeline of creation is not what we thought. And if the internal structure of galaxies is backwards from our models, then the structure of space itself, on the grandest scales, may also be hiding something we have not accounted for. In January of 2026, a team of scientists published the most detailed map of dark matter ever created. It was built using data from James Webb's Cosmos Webb survey, the largest observing program Webb undertook in its first year. The survey covered a patch of sky roughly 2.5 times the area of a full moon. And within that patch, Webb measured the shapes of 129 galaxies per square arc minute. That density of measurement, combined with Webb's extraordinary resolution, allowed the team to construct a dark matter map with more than twice the sharpness of any map built from Hubble data. Dark matter cannot be photographed directly. It emits no light and reflects none. It does bend light through gravity. When light from a distant galaxy passes through or near a concentration of dark matter, the dark matter's gravity warps the path of that light, distorting the apparent shape of the background galaxy in a subtle but measurable way. By carefully analyzing the shapes of hundreds of thousands of galaxies across a wide field, scientists can work backwards and calculate where the dark matter must be to produce those distortions. This technique is called weak gravitational lensing. Webb's new map revealed something important. Dark matter and ordinary matter, the stars and gas we can see, have been evolving together throughout the history of the universe. Wherever the dark matter map shows a dense concentration, the visible galaxy map shows a matching cluster. Wherever the dark matter shows an empty region, the galaxy distribution shows a corresponding gap. The two tracings of structure are deeply correlated, confirming that dark matter's gravity has been the primary sculptor of the visible universe since the very beginning. The map also showed something subtler and more interesting. At the scale of individual galaxy clusters and the filaments between them, some dark matter structures appeared smaller and sharper than earlier, lower resolution maps had suggested. What previously looked like broad, diffuse clumps resolved, under Webb's sharper eye, into tighter concentrations. Some structures that had seemed large and smooth turned out to contain internal detail that changes how scientists interpret their mass distribution. This matters because the size and density profile of dark matter structures is one of the key predictions that different dark matter models make. Cold dark matter predicts compact, cuspy concentrations. Warm dark matter predicts smoother, more spread out profiles. The new map's data will take time to fully analyze, but it gives scientists a tool to test these predictions with a precision that was not available before. The map also traces dark matter across a range of cosmic distances, allowing researchers to see how the structure has evolved over billions of years. The pattern they see is one of continuous co-evolution, dark matter and visible matter building the universe together, each tracing the other's presence across deep time. What we have now is a timeline of how the hidden skeleton of the universe was assembled, and it raises a question that cuts to the heart of what Webb is revealing. If the skeleton formed earlier and faster than our models predict, and if the galaxies hanging on it are more massive and more organized than they should be, then what else about the universe's structure have we been reading wrong? Something even stranger is hiding in the spaces between the threads. Between the threads of the cosmic web, there is nothing. Regions of space so empty of galaxies, so devoid of stars and gas and even dark matter concentrations that they stretch across distances measured in hundreds of millions of light years. These regions are called cosmic voids, and they are one of the most underappreciated structures in the observable universe. We know they exist. Large-scale galaxy surveys have been mapping them for decades. The cosmic web, when viewed in 3 dimensions, looks like a foam of soap bubbles. The thin walls and filaments of galaxies form the surfaces of those bubbles. The interiors of the bubbles are the voids, empty, vast, profoundly quiet. Here is what has become a growing concern in cosmology. The voids that surveys are finding are larger than the standard model predicts, and the discrepancy is consistent. The standard cosmological model, given the initial conditions set by the Big Bang and the known physics of dark matter and dark energy, makes predictions about the statistical distribution of void sizes across the universe. How many small voids should exist? How many medium ones? How rare the very large ones should be? For years, these predictions appeared to hold reasonably well. As surveys have grown more comprehensive, mapping larger volumes of the universe with greater precision, a pattern has emerged. The very largest voids are more common than the model predicts. The distribution is consistently off in one direction. There are more giant voids than there should be. The most famous example is a structure called the Bouteille's void, discovered in 1981, a roughly spherical region of space, approximately 330 million light-years across, that contains almost no galaxies. Under the standard model, a void of that size, in a universe of that age, should be extraordinarily rare, possibly unique. Yet subsequent surveys have found other voids approaching similar scales. More recently, surveys building on data from James Webb and complementary ground-based telescopes have been extending void measurements to greater distances, looking at voids in the early universe to compare their sizes with predictions at different cosmic ages. The emerging picture is of a universe whose empty regions expanded faster than the models account for, leaving behind bigger gaps in the cosmic foam than expected. One possible explanation is that dark energy was stronger in certain periods than the standard model assumes. If expansion accelerated more vigorously in some epochs, it would have stretched the voids faster and to greater sizes than a constant dark energy model predicts. Another explanation brings us back to dark matter. If dark matter is warmer or more wave-like than the cold dark matter model assumes, the way structure forms and the way voids grow between that structure would both be affected. A smoother, dark matter distribution produces a different void size spectrum. The voids are measurements, precise records of how fast expansion has been working against gravity across cosmic time. Each giant empty bubble is a timestamp, a record frozen in space of how forcefully expansion pushed matter away from a given point. And right now, those measurements are telling us that something in our model is running faster than it should. What Webb has shown about the light reaching us from across the universe raises a possibility that cuts even deeper. Some of what we see may not be real at all. Light travels in straight lines. That is what we are taught. And in everyday experience, it is true. Shine a flashlight across a room and the beam goes straight. Everyday experience does not include the presence of enormous masses bending the fabric of space itself. Einstein's general theory of relativity, published in 1915, made a prediction that seemed almost impossible at the time. Mass curves space. Curved space curves the path of light. A beam of light passing near a massive object does not travel straight. It follows the curve of the space that object creates, bending toward the mass, emerging on the other side, pointed in a slightly different direction than it entered. This was confirmed experimentally in 1919 during a solar eclipse, when astronomers measured the apparent positions of stars near the edge of our star's disk and found them shifted by exactly the amount Einstein's equations predicted. Space was a dynamic medium, warped by everything that existed within it. For cosmology, this has a profound consequence. When we look at a distant galaxy, the light from that galaxy does not travel to us through empty, flat space. It travels through a universe filled with galaxy clusters, dark matter concentrations, and the filaments of the cosmic web, all of which are bending that light as it passes. By the time it reaches our instruments, it has been deflected, distorted, magnified, and sometimes split into multiple images by every mass concentration it encountered along the way. This effect is called gravitational lensing. It comes in two forms. Strong lensing produces dramatic, visible effects. A distant galaxy aligned behind a massive cluster can be stretched into arcs, rings, or multiple copies of itself, each one a different path that light took around the intervening mass. James Webb has captured some of the most spectacular examples ever seen, including a galaxy cluster so massive it produced 5 separate images of a single background galaxy pair, arranged into a cosmic question mark shape. Weak lensing is subtler, but far more powerful as a scientific tool. Every galaxy we see is slightly distorted, its shape stretched or compressed by the dark matter and ordinary matter between us and it. No individual distortion is large enough to detect, but by averaging over hundreds of thousands of galaxies and looking for statistical patterns in their shapes, scientists can map the mass distribution along the line of sight. This is how the dark matter maps are built. And here is the unsettling part that rarely gets discussed outside of technical papers. Gravitational lensing means that what we see is not necessarily what is there. The apparent position of a galaxy in the sky is not its true position. Its apparent brightness is not its true brightness. Its apparent shape is not its true shape. Every measurement we make of every object in the deep universe has been altered, to some degree, by the mass distribution between us and it. We do not see the universe directly, we see a projection of it through a lens that is never perfectly flat. For most purposes, this distortion is small and calculable. Scientists account for it. When Webb looks at the very early universe, it is looking through 14 billion years of accumulated cosmic structure, all of it bending the light that carries information about the dawn of time. What we see when we look that deep is real. It is also, in a precise and technical sense, an illusion, a bent, stretched, distorted image of a reality we can never observe directly. That realization changes the meaning of everything Webb is showing us. Consider what a map is. A map is a representation of reality. A street map of a city tells you where the roads go, but it does not tell you about the traffic, the potholes, the buildings that were demolished last year. Every map is an approximation, built from measurements that have errors and a perspective that has limits. The map we have of the universe, built from decades of telescope observations, is the most complex and precisely constructed map in human history. James Webb has made it undeniably clear that this map is a distorted image, curved, stretched, and filtered in ways that we are only beginning to fully account for. Gravitational lensing is a fundamental feature of observation itself at cosmological distances. Every deep field image that Webb captures, every survey of early galaxies, every measurement of the cosmic microwave background, all of it has been shaped by the gravity of everything that lies between us and the source. In 2024, Webb detected one of the most extreme examples of gravitational lensing ever observed. A background galaxy, located billions of light years behind a massive foreground cluster called Max J 417, was imaged 5 separate times, each image a different path that the galaxy's light had taken around the intervening mass. The 5 images were arranged in a pattern called a hyperbolic umbilic, one of only 3 or 4 such configurations ever identified in the observable universe. The background galaxy appeared as a cosmic question mark, its light bent into an almost artistic distortion. That image is beautiful. It is also a reminder. What we are seeing is 5 slightly different versions of the galaxy's light, each one bent, magnified, and delayed by a different amount, arriving at Webb's mirror after traveling slightly different paths through distorted space. Now scale that up. Hundreds of thousands of galaxies behind thousands of clusters, behind millions of dark matter concentrations. Every image in every Webb deep field photograph has been touched by gravitational lensing, some lightly, some significantly. All of it adding layers of distortion between what the universe looks like and what we measure. The practical consequence is that any map we draw of the large-scale structure of the universe, any picture of the cosmic web, any measurement of void sizes or filament lengths, is a projection through a medium that bends and distorts. We are doing the best we can with extraordinary tools. The image we are building is the universe as seen through a gravitational lens that spans all of space. Some researchers have begun exploring whether the Hubble tension itself could be partially a gravitational lensing artifact. If the region of space between us and the distant standard candles we use to measure expansion has a slightly different mass distribution than our average models assume, it could introduce a systematic bias into our distance measurements. The effect would be small, but small effects compounding across cosmic distances can produce exactly the kind of persistent discrepancy we see. This remains an active area of research. It has not resolved the Hubble tension. It adds another layer to the puzzle. The universe, seen through 14 billion years of bending space, may look subtly but systematically different from what it actually is. And if that is true at the scale of galaxy distances, what does it mean at the largest possible scale? At the scale of the universe's entire shape and geometry. When cosmologists talk about the shape of the universe, they are not talking about its outline. They are not asking whether it looks round or square from the outside. That question does not even make sense in the framework of modern cosmology, because the universe, as far as we can determine, has no outside. It does not exist inside a larger container. Space itself is the thing, and asking what shape it has from outside is like asking what is north of the North Pole. The question needs to be rephrased. What cosmologists are actually asking is this: what is the geometry of space on the largest scales? If you drew a straight line through the universe and followed it far enough, would it eventually curve back around on itself? And if you drew a giant triangle across billions of light years of space and measured its angles, would they add up to more than 180 degrees, less, or exactly 180 degrees? These questions have 3 possible answers. The universe could be positively curved, like the surface of a sphere. In that geometry, parallel lines eventually converge, and a large enough triangle has angles that add up to more than 180 degrees. A universe like this is finite, with no edges, and wraps around on itself like the surface of a ball. The universe could be negatively curved, like the surface of a saddle. In that geometry, parallel lines diverge, and triangles have angles that add up to less than 180 degrees. A universe like this is infinite and open. Or the universe could be flat. Parallel lines stay parallel forever. Triangles sum to exactly 180 degrees. The universe extends infinitely in all directions, without curving. The best measurements we have, based on the detailed structure of the cosmic microwave background radiation, suggest that the universe is flat to within our best precision. The standard model predicts flatness, and the data confirms it. There is a catch. Our measurements of the universe's geometry are limited by what we can observe. The observable universe, the sphere of space from which light has had time to reach us in 14 billion years, is enormous. It is almost certainly a tiny fraction of the total universe. If the universe is vastly larger than the observable portion, it could have a slight overall curvature that is simply too gentle to detect within the region we can see. Just as Earth's surface appears flat when you are standing on it, the universe's curvature could be too large scale to measure from our current vantage point. James Webb is now providing measurements that reach further back in time and with greater precision than anything before it. Researchers are examining whether the curvature measurements hold at earlier cosmic ages the same way they do today. So far, the data supports flatness. The precision required to detect a very slight curvature is at the absolute edge of what is technically possible. And there are theoretical reasons to suspect the universe might not be as simple and uniform as the flat, infinite model suggests. Reasons that come directly from what happens when you apply quantum mechanics to the Big Bang itself. The evidence pointing in that direction may be closer than you think. One of the foundational assumptions of modern cosmology is called the cosmological principle. It states that the universe, on the largest scales, is homogeneous and isotropic. Homogeneous means it looks roughly the same from every point. Isotropic means it looks roughly the same in every direction. No special places, no special directions. On the grandest scales, the universe is a smooth, even distribution of matter and energy, with the structures we see, galaxies, clusters, filaments, being statistical fluctuations around that even average. This principle is not an arbitrary assumption. It is motivated by theory and supported by observation. The cosmic microwave background, the oldest light in the universe, is remarkably uniform across the sky. The temperature varies by only tiny fractions of a degree from one patch of sky to another. That uniformity is one of the strongest pieces of evidence that the early universe was smooth and that the large-scale average of the current universe remained so. Observations are now beginning to reveal cracks in that uniformity. One of the most studied is a feature called the cold spot. In the cosmic microwave background radiation, there is a region of sky in the constellation Eridanus that is measurably colder than average, covering an area far larger than statistical models predict should exist. Various explanations have been proposed, including a supervoid in the foreground, whose gravity removes energy from microwave photons passing through it. The supervoid explanation requires the void to be among the largest known structures in the observable universe. Beyond the cold spot, surveys of galaxy distributions have revealed large-scale patterns that push against the cosmological principle. The Sloan Great Wall, a vast filament of galaxies stretching nearly 1.25 billion light-years. The Hercules Corona Borealis Great Wall, an even larger concentration spanning roughly 10 billion light-years. These are at or beyond the scale at which the cosmological principle predicts the universe should become smooth. Their existence as coherent structures at those scales is difficult to reconcile with standard models. James Webb is now contributing to this picture by extending large-scale structure measurements to earlier cosmic epochs. As Webb maps the distribution of galaxies at greater distances and earlier times, it is testing whether the universe's large-scale uniformity holds across cosmic history, or whether there are deviations that accumulate or fluctuate with time. The early data is not definitive. The consistent appearance of structures in Webb's deep fields that are more organized and more clustered than standard models predict at those distances adds to the growing list of reasons to question whether the cosmological principle holds as cleanly as assumed. A universe that is less uniform than we believed has a different history than the one we have been reconstructing. It suggests that the initial conditions of the Big Bang, or the physics of the earliest moments, left imprints in the structure of space that our standard model is not capturing, and those earliest moments, the first fractions of a second after the Big Bang, are where one of the most radical proposed solutions to all of these puzzles is rooted. A solution that involves a type of energy that existed only briefly in the very first moments, and then vanished without leaving a clear signature behind. What was injected into the universe at the very beginning may have been changing the rules ever since. Imagine the universe in its first moments. A fireball smaller than a grain of sand, hotter than anything that has existed since, expanding at a rate that dwarfs anything we observe today. In those first fractions of a second, the physics operating was so extreme that our current equations break down. We cannot describe what happened at the very beginning. We can only describe what happened after things cooled enough for familiar physics to take over. For decades, cosmologists assumed that the transition from that extreme beginning to the universe we can model was relatively smooth. The universe expanded, cooled, and the various forces and particles settled into the pattern described by the Standard Model. No major surprises, no hidden kicks or jerks in the expansion history. The Hubble tension is pointing directly at that assumption and asking hard questions. Remember the core problem. The early universe measurements give a lower expansion rate. The late universe measurements give a higher one. Webb confirmed both are accurate. Something must explain the gap. One of the leading theoretical proposals to resolve this gap is called early dark energy. The idea is that in the period shortly after the Big Bang, before the universe had cooled enough to form atoms, there was a brief but powerful injection of extra energy into the cosmic expansion. This energy, similar in character to dark energy but existing only temporarily, accelerated the universe's expansion during a window of time that left no direct signature in the cosmic microwave background we observe today. After that window closed, the early dark energy faded away, and the universe settled back into the expansion history the Standard Model describes. If early dark energy existed, it would have compressed the distances between objects during the early universe, slightly more than the Standard Model accounts for. That compression would cascade through the calculations, making the predicted expansion rate for the current universe higher than the background radiation-based measurement suggests. In other words, it could close the gap in the Hubble tension. Mark Kamionkowski, a cosmologist at Johns Hopkins University who helped calculate the Hubble constant and has been one of the architects of the early dark energy proposal, described the tension as a potential signal that something is missing in our understanding of the early universe, a new component of matter or energy that gave the universe an unexpected kick. The early dark energy hypothesis has attracted significant attention and significant criticism in equal measure. Proponents point out that it fits the Hubble tension data well and makes specific predictions about the cosmic microwave background that future experiments can test. Critics argue that it requires fine-tuning to work, that the energy must appear and disappear at precisely the right moment, and that such fine-tuning is a red flag in physics, suggesting an incomplete understanding rather than a true solution. As of early 2026, the debate is unresolved. No measurement has definitively confirmed or ruled out early dark energy. The fact that hundreds of cosmologists are taking it seriously is itself a statement about the state of the field. The Standard Model is failing loudly in multiple independent measurements across multiple independent teams in a way that demands a real physical explanation. And the explanations being considered are no longer minor adjustments. They involve new physics, unknown energy, particles that may not yet have names. Physics has been here before. In the late 19th century, the dominant theory of light required a medium for light to travel through, something called the luminiferous ether that filled all of space. When the Michelson-Morley experiment failed to detect any trace of this ether in 1887, the result was treated initially as a puzzle, then as a crisis. The solution turned out to be something nobody had anticipated: special relativity, Einstein's reframing of space, time, and motion that overturned a century of assumptions. In the 1920s, physicists discovered that atoms did not behave the way classical mechanics predicted. Electrons did not orbit nuclei like planets around a star. They existed in quantum states, governed by probability rather than fixed trajectories. The solution was quantum mechanics, a framework so strange and counterintuitive that Einstein himself refused to fully accept it. Yet it turned out to be the most precisely tested theory in the history of science. Every time physics has hit a wall this fundamental, the solution has required expanding the framework, replacing part of it with something larger and stranger. The Hubble tension, the overmassive early galaxies, the wrong-shaped dark matter structures, the two large voids, and the mysterious bright objects that defy current brightness limits. Taken together, these are beginning to look like the kind of wall that demands a new framework. The proposals currently on the table range from conservative to radical. On the conservative end, early dark energy requires no new particles or forces, only a temporary component of energy in the early universe. If confirmed, it would extend the existing framework without fundamentally breaking it. More ambitious proposals involve modifying the behavior of dark energy itself. The current standard model assumes dark energy is a constant, a fixed term in Einstein's equations that produces a steady, unchanging acceleration of expansion. Some models propose that dark energy is dynamic, that it grows or shrinks over time, that it behaves more like a field, with a value that evolves as the universe ages. These models, sometimes called quintessence models, predict subtle variations in the expansion history that current and upcoming surveys are beginning to have the sensitivity to test. Still more radical proposals involve modifying gravity itself. General relativity has been tested with extraordinary precision within our solar system and in the vicinity of neutron stars and black holes. It has never been tested on the scale of hundreds of millions of light years across the cosmic web in the conditions of the early universe. Some physicists propose that gravity behaves differently on those scales in ways that our current equations do not capture. And then there are proposals that go further still. Extra dimensions of space that become relevant at cosmological scales. New families of particles interacting only through gravity, or mirror universes running parallel to ours, whose gravitational influence leaks into our observable cosmos. These ideas exist at the boundary between physics and speculation. They are not mainstream. They are not dismissed either, because the data is becoming serious enough that serious people are considering serious possibilities. James Webb cannot directly test most of these proposals. What it can do, and is doing, is provide the precise measurements of the early universe that constrain which proposals survive and which do not. Every galaxy mass it measures, every cosmic web filament it traces, every anomalous bright object it catalogues, is a data point that narrows the space of possible solutions. The universe is telling us something. We do not yet know what, but the scale of what we are being told is becoming clear. Stop for a moment and consider the scale of what we have been discussing. James Webb can see back to within a few 100 million years of the Big Bang. That means the light it captures has been traveling toward us for roughly 13.5 billion years. In that time, the expansion of the universe has carried the source of that light to a current distance of about 46 billion light-years. The observable universe, the sphere of space from which any signal could have reached us since the Big Bang, has a radius of approximately 46 billion light-years. That is the observable universe. It contains an estimated 2 trillion galaxies, each with billions of stars, across a volume that is almost impossible to hold in the imagination, and it may be a tiny bubble inside the actual universe. This is a mathematical consequence of the standard model itself. The theory of cosmic inflation, which describes an extremely rapid, exponential expansion of space in the first moments after the Big Bang, predicts that the total universe is vastly larger than the observable portion. Some versions of inflation predict the total universe is incomprehensibly larger than what we can see. Larger by a factor that makes any number we might write seem meaningless. In practical terms, this means the patterns we observe in the cosmic microwave background, the flatness of space, the uniformity of the universe on large scales, are all features of our particular bubble. Other regions of the total universe, regions so far away that no light from them has ever reached us and never will, may have different properties, different physical constants, different histories, perhaps different laws. This is the framework behind the concept of the multiverse, and it is important to be precise about what is and is not scientific here. The existence of regions beyond our observable horizon is a mathematical prediction of inflation theory, not a confirmed observation. We can test inflation's predictions about what our observable universe should look like, and those tests have generally supported it. The regions beyond our horizon are by definition unobservable, which means the multiverse scenario cannot be directly confirmed or falsified. What James Webb is doing is testing inflation's predictions more precisely than ever before by studying the very early universe. If the patterns it finds in the structure of the first galaxies, the cosmic web, and the large-scale distribution of matter match what inflation predicts, that supports the overall framework. If the patterns deviate, it challenges both inflation and the multiverse picture derived from it. Right now, Webb's findings are creating tension. The early universe looks more structured, more organized, and more complex than the simplest inflationary models predict. This does not rule out inflation. It may be telling us that inflation was more complex than assumed, that it had multiple phases, or that the initial conditions it generated were different from what our current models describe. We are standing on one grain of sand, trying to understand the beach. Our entire observable universe, with its 2 trillion galaxies and its billions of years of history, is that grain. The beach stretches in every direction beyond what any instrument will ever reach. The grain of sand has a telescope, and the telescope is asking questions that the beach is struggling to answer. There is a wall, nothing you could touch or approach. A boundary in time and space, beyond which no information will ever reach us, no matter how powerful our instruments become. It is called the cosmological horizon, and it is the ultimate limit of what any telescope, including James Webb, can ever observe. It exists because the universe has a finite age. Roughly 14 billion years have passed since the Big Bang. Light travels at a fixed speed. Therefore, only light that has had 14 billion years to travel can possibly have reached us. Objects further away than that are invisible to us forever. They are beyond the horizon. The cosmological horizon is not just a distance limit. Because the universe is expanding, the light from objects near the edge of the observable universe is being carried away from us faster than it is traveling toward us. The most distant galaxies Webb can detect are not standing still while their light slowly crosses the distance between us. They are being swept further away by the expansion of space itself. Some of them are now so far away that even if they emitted light today, that light would never reach us. The expansion of space between us and them is faster than light can cross. There are objects that exist right now, real galaxies with real stars, that are permanently beyond any possible observation. They are separated from us by the geometry of an expanding universe, a boundary that has nothing to do with distance in any conventional sense. James Webb is looking as close to that wall as any instrument ever has. Its most distant, confirmed observations reach back to galaxies that formed within the first 400 million years of the Big Bang. Beyond that, there was a period called the Epoch of Reionization, during which the universe was still filled with neutral hydrogen gas that blocked the passage of most light. Webb can look into that fog, but not through it entirely. And before the Epoch of Reionization, there was a period called the Cosmic Dark Ages. The universe had cooled enough for atoms to form, but not yet enough for stars. There was no light at all. Complete darkness, stretching for hundreds of millions of years, filled with hydrogen and helium gas, slowly collapsing under gravity into the first protostars. Webb cannot see into the Dark Ages. No optical or infrared telescope can. The first stars of that era have not been directly detected. We see the results of what happened in the Dark Ages, the galaxies and structures that emerged from it, but not the process itself, what lies in and beyond the Dark Ages, in the first moments after the Big Bang, when the physics was so extreme that our equations fail, remains genuinely unknown in the sense of being outside the reachable universe entirely. This is the honest acknowledgement of a fundamental limit, and it is a limit that gives the cosmos its most profound quality. The universe is larger than the knowable. What we can observe, what Webb can map and measure and analyze with its golden mirror, is a small window into something that extends beyond any possible window. And in that small window, enough has been found already to suggest that even what we can see is stranger than we were prepared for. If the standard model of cosmology needs to be fundamentally revised, the consequences reach further than the equations. They reach into how we understand time itself. The standard model tells us the universe is approximately 13.8 billion years old. That number comes directly from the expansion rate, the Hubble constant, and from the detailed structure of the cosmic microwave background. It is a precise calculation based on a specific model of how the universe evolved. The Hubble tension means the expansion rate is uncertain. And if the expansion rate is wrong, the age of the universe may be wrong. A higher actual expansion rate would imply a younger universe. A different early dark energy history could shift the calculation in either direction. More fundamentally, the overmassive early galaxies that Webb has been finding are directly relevant here. Under the standard model's timeline, there is simply not enough time for those galaxies to have formed at the age we observe them. If the galaxies are real, and they are, then either the formation process was radically faster than assumed, or the universe was older than we calculated when those galaxies formed, or both. Each possibility carries enormous consequences for how we reconstruct the history of everything. The origin story itself is at stake. How the first stars formed, what ignited the epoch of reionization, when the first black holes seeded and how they grew, how the cosmic web assembled. The entire narrative of cosmic history, from the Big Bang to the present, is built on the framework of the standard model. If that framework is substantially wrong, the narrative needs to be rewritten from the first chapter. There is a deeper dimension here as well. The standard model of cosmology is not just a scientific framework, it is the closest thing humanity has to a verified creation story. It tells us where we came from. It places our existence in a context that stretches back 14 billion years to a single, incomprehensibly hot origin point. It tells us that every atom in our bodies was forged in the interior of stars that died before our star was born. It gives us an account of our origins grounded in evidence rather than mythology. If that account is incomplete, if it is missing a major component, if the first chapter is not what we thought, then we are in a moment that is genuinely rare in the history of knowledge. A moment when the best tested framework in science is being challenged by its own best instruments, and the outcome is not yet clear. This kind of moment has happened before in science, and every time it did, the resolution required a framework so different from what preceded it that the people who built the old one could barely recognize what replaced it. John O'Meara, chief scientist at the Keck Observatory, articulated the stakes plainly when discussing the Hubble tension. Cosmology, as we know it, he said, may be broken, and if it is broken, we will have to come up with new physics. New physics, that phrase carries the weight of everything Webb is finding. A new description of how the universe works. The scale of what comes next is exactly as large as what came before, and the universe has never once apologized for that. Science is not a collection of answers. It is a method for asking better questions. Every instrument humanity has ever built to look at the universe has produced two things: answers to the questions it was designed to answer, and new questions that nobody thought to ask before. Galileo's telescope revealed moons around Jupiter and destroyed the idea that everything orbits the Earth. Edwin Hubble's observations revealed that the universe was expanding and immediately raised the question of what it was expanding from and into. The Hubble Space Telescope revealed the deep structure of galaxies and sparked a revolution in cosmology that is still unfolding. James Webb was designed to look further and clearer than anything before it. It has done that. It has also, in the process, opened more questions than it has closed. The scientists working with Webb data are not discouraged by this. They are electrified. The questions Webb is raising are the right kind. Specific, testable, pointing at real gaps in real models. Precise discrepancies that demand precise solutions. Several major scientific programs are already underway to follow where Webb is leading. The Euclid Space Telescope, launched in 2023, is conducting the largest survey of galaxy shapes and positions ever attempted, covering 1/3 of the sky and measuring billions of galaxies to map the cosmic web and dark energy with unprecedented precision. The Nancy Grace Roman Space Telescope, planned for launch in the coming years, will combine sharp image quality with a field of view 200 times larger than Hubble's. Extending the dark matter mapping work Webb has begun across a vastly greater volume of the universe. The Vera Rubin Observatory in Chile, which began operations in 2025, is conducting a 10-year survey of the southern sky that will detect billions of galaxies and provide a completely independent measure of the universe's expansion history. The next generation of cosmic microwave background experiments is being planned to measure the Big Bang's afterglow with a precision that will either confirm or rule out early dark energy at a definitive level. Webb itself continues to operate. Its cryogenic coolant supply and orbital stability suggest it may remain scientifically productive for 20 years or more. Every year it operates, it adds to the catalogue of early galaxies, little red dots, cosmic Webb filaments, and anomalous objects that are building the case for new physics. That framework does not yet exist. It may look nothing like what any physicist today imagines. It may require a conceptual leap as large as quantum mechanics or general relativity, a new way of thinking about space, time, matter, and energy that makes our current models look like rough approximations. What is certain is that the universe has not run out of surprises. Every generation of astronomers has looked at the sky with the best tools available and believed, for a moment, that the picture was nearly complete. Every generation has been shown otherwise. The universe simply contains more than any single framework can capture, and it keeps offering more data to anyone willing to build a better eye. James Webb is that eye. It is looking, and what it is finding, at the edge of time, in the light that has been travelling for nearly 14 billion years to reach a mirror of gold in the cold dark beyond the moon, is telling us something we are only beginning to understand. The universe is stranger, larger, and more mysterious than the map we spent 50 years building. Somewhere in that strangeness, somewhere in all of it, is the true shape of everything. We are just learning how to see it.